Building and maintaining roads and bridges ensures safe travel, connects communities, and shapes the backbone of modern infrastructure. Installing a soil cement diaphragm wall with a Chemrock KSI 12000 begins by mounting the mixing attachment onto a standard excavator. The KSI's cutting chain penetrates the ground to the required depth, while a cement-based binder is injected at the blade's lowest point. As the chain rotates, it thoroughly mixes the suspension with the in-situ soil, forming a uniform and stable soil cement mass. By steadily advancing along the alignment, the system produces a continuous, impermeable diaphragm wall directly in the ground, avoiding excavation, soil removal, and backfilling, and significantly reducing construction time and material use. Working with a Steelwrist grading beam greatly enhances the efficiency and precision of excavator operations. The grading beam is designed for leveling and compacting large surfaces, often serving as the final preparation step before construction or paving. When paired with a Steelwrist tiltrotator, the tool becomes exceptionally versatile, allowing the operator to push, pull, and smooth material without repeatedly repositioning the excavator. The tiltrotator provides full 360-degree rotation and up to 45-degree tilt, enabling advanced grading around obstacles and across uneven elevations. This combination helps achieve consistent surface quality while reducing time and fuel consumption. Many grading beam models also feature adjustable side panels that improve material control and productivity. Overall, the Steelwrist grading beam system delivers faster, more accurate earth-moving performance on modern job sites. Installing a box culvert begins with careful site preparation. The crew excavates the trench to the required depth and width, removes soft spots, controls groundwater, and creates a stable, level base using compacted granular material or a PCC layer. Once the foundation is ready, workers begin placing the culvert sections from the outlet side, inspecting each unit and applying butyl mastic sealant to the joints. The sections are then aligned to maintain proper line and grade, with bottom pieces typically set before top units. After the full run is connected, the team constructs the headwalls, backfills and compacts the surrounding soil in layers, and finally restores the surface, ensuring the installation meets all design and quality requirements. Building a road from the ground up begins with a detailed study of the topography to evaluate the existing soil strength and determine how much material must be cut or filled. Before construction starts, designers also assess potential impacts on traffic flow and the surrounding environment. These considerations help define the most suitable road layout, including lane numbers, alignment, and pavement thickness. After the design is approved, the contractor clears the site of vegetation and debris. Depending on elevation changes, crews carry out cut and fill operations to achieve the required grade. The soil is then thoroughly compacted to provide a stable foundation capable of supporting the roadway and future traffic loads. A grader shapes the final slope of the subbase. Next, underground utilities such as electrical lines, water systems, and drainage networks are installed. Stormwater pipes and catch basins are placed along the roadway to direct runoff into larger drainage systems or detention ponds. With utilities complete, construction of the road structure begins, starting with a stone aggregate base whose thickness varies with traffic demands. Asphalt is then laid in multiple layers, compacted and cooled. Finally, Lane markings, reflectors, signs, and guardrails are installed to complete the roadway. An asphalt plant operates by combining stone, sand, and recycled materials with liquid asphalt to produce durable pavement mix. The process begins at the stockpiles, where aggregates of different sizes are stored. A loader transports these materials to the cold feed bins, each designated for a specific aggregate size. Conveyors move the aggregates into the plant, where the operator adjusts the mix proportions from the control room. The materials then enter a large rotating drum, heated by a gas burner, which dries them completely. After drying, liquid asphalt from heated storage tanks is injected into the drum, allowing thorough mixing. Reclaimed asphalt pavement can also be added through a separate feed system, reducing cost and environmental impact. In continuous drum plants, drying and mixing occur in the same drum, while batch plants mix in a separate chamber. Once prepared, the hot asphalt is stored in silos and loaded into trucks for delivery to paving sites. Improving efficiency through a partnership forged in steel is essential, as mining operations expand to support the growing needs of the Jamshedpur and Kalinganagar steel plants. To meet the rising demand for fines, Tata Steel required a partner with complete expertise and the ability to handle site-specific challenges. At Kanband, the ore has a very high tumbler index, making specialized crushing and screening units necessary to achieve the desired size and quality. Moreover, the need to beneficiate lower-grade materials is becoming increasingly important. This led to a lifecycle services contract with Metso India, covering logistics from the mine face to final delivery. Metso meets strict safety expectations, ensures reliable production of fines, and provides world-class equipment capable of efficient system changeovers. The Route 58 Rehabilitation Project in Southampton County, Virginia, introduces an innovative approach to road construction by replacing traditional asphalt overlays with hydraulic cement concrete pavement. The Virginia Department of Transportation, which has long relied on asphalt, is now testing this new alternative to reduce dependence on oil-based materials and mitigate the effects of fluctuating oil prices. In this project, a continuously reinforced concrete pavement is applied, eliminating the need for joints that typically cause the repetitive chunk ch noise of conventional concrete roads. The embedded steel reinforcement keeps cracks tightly closed, ensuring a smoother and more durable surface for motorists. The construction process involves an unbonded concrete overlay technique. First, the existing pavement is shot blasted to remove oil, dirt, and debris, creating a rough surface for better adhesion. Fresh concrete is then delivered from the batching plant and spread evenly across 2 lanes using a paving machine. Subsequent equipment ensures proper compaction and uniform thickness. Finally, a curing compound is applied, and fine grooves are raked into the surface to improve traction and safely drain water from the roadway. Advanced GPS technology precisely guides the paving machines, ensuring accurate alignment and consistent pavement thickness. This efficient method not only provides a smoother ride, but also offers VDOT engineers a cost-effective and sustainable alternative for future projects. The Virginia Center for Transportation Innovation and Research will continue to monitor the performance of this new hydraulic cement concrete pavement to evaluate its long-term success. The concrete paving operation shown in Thailand demonstrates a practical and well-coordinated method for constructing durable road surfaces under local working conditions. The process begins with preparing the subbase, which is carefully graded, leveled, and compacted to provide a stable foundation for the upcoming 0.25-meter thick concrete layer. Once the formwork is placed along both sides of the lane, workers inspect the alignment to ensure the correct width, elevation, and slope of the pavement. As ready-mixed concrete arrives on site, it is discharged directly onto the prepared section. In the image, teams of workers immediately spread the fresh mixture using long-handled rakes and shovels. This manual spreading is essential to achieve a uniform distribution before mechanical consolidation takes place. The workers move efficiently across the surface, ensuring that the concrete reaches all corners of the formwork and that no voids remain, especially near the edges. After the initial spreading, the crew performs vibration and leveling. A vibratory screed, visible at the front of the working area, moves slowly along the rails, compacting the concrete while striking off excess material. This step is crucial because proper vibration removes trapped air, increases density, and significantly improves the pavement's long-term strength. Behind the screed, workers continue adjusting the concrete surface, guiding the equipment, and correcting any low spots or uneven areas. Following the primary leveling, the finishing stage begins. Workers smooth the surface using bull floats and hand tools, creating a consistent texture while closing surface pores. This step not only enhances the appearance of the pavement, but also improves its durability and resistance to moisture penetration. Depending on project requirements, a broom finish may be applied afterward to provide skid resistance for vehicles. Once the surface is completed, curing begins immediately to prevent rapid moisture loss in Thailand's hot climate. Water curing, curing compounds, or protective coverings may be applied to maintain adequate hydration during the early stages of hardening. Proper curing ensures that the pavement reaches its designed strength and extends its service life. Overall, the process reflects a coordinated blend of manual labor and mechanical tools, resulting in a strong, resilient concrete roadway suitable for Thailand's traffic demands and environmental conditions. Designing and constructing an asphalt parking lot involves a carefully coordinated process that brings together engineering principles, material science, and best construction practices. Because asphalt pavements function as layered systems, each layer, subgrade, aggregate base, and asphalt courses contributes to the overall strength and long-term performance of the structure. Modern pavement design relies heavily on software tools such as Pave Express, which enable engineers to determine the proper material thicknesses for expected loading conditions. Two key parameters dominate this calculation: the quality of the subgrade soils that provide foundational support, and the magnitude and frequency of traffic loads that the pavement will sustain. Naturally, areas exposed to heavy truck traffic require much thicker pavement sections than those designated for passenger vehicles. Parking lots are commonly built on native subgrade soils, which must be well compacted at the correct moisture content to form a stable working platform. Clay-rich subgrades are especially sensitive and must be conditioned properly before any structural layers are added. Once evaluated, unsuitable soils are removed or stabilized, ensuring the foundation can support the intended loads. Effective drainage planning is equally critical. Many pavement failures are caused not by traffic, but by trapped stormwater. For this reason, designers must incorporate both surface and subsurface drainage strategies. The pavement surface is typically sloped a minimum of 2% to prevent ponding, while under-drained systems channel infiltrated water away from the subgrade. Material selection plays a central role in achieving durability. Asphalt mixtures are composed of mineral aggregates and liquid asphalt binder, blended to create a waterproof, stone-on-stone framework. Because parking lots experience slower speeds and significant turning movements, their mixtures are often formulated with higher asphalt binder content than roadway mixes. Designers may also incorporate warm mix asphalt technology, which allows production and placement at significantly lower temperatures, reducing emissions and improving workability. Additionally, reclaimed asphalt pavement and recycled shingles are frequently included to reduce the use of virgin materials while enhancing mixture stiffness and resistance to tire scuffing. Construction begins after the subgrade and aggregate base have been placed and compacted to specification. A qualified paving contractor uses a self-propelled paver to place asphalt in smooth, uniform layers while avoiding segregation. Base asphalt mixtures, which contain larger aggregates, are placed in thicker lifts and compacted immediately. Proper compaction is essential. The finished layer thickness must meet design requirements, and each lift must be at least 3 times thicker than the largest aggregate size to achieve adequate density. Before the final surface course is placed, a tack coat is applied to ensure a strong bond between layers. The surface asphalt is then laid and compacted until roller marks disappear, and the specified density and grade are achieved. When properly designed, drained, and constructed, an asphalt parking lot can deliver decades of reliable service with minimal maintenance. Spotline is a Type 2 road marking system that combines PlastiRoute cold plastic, UCME drop-on glass beads, and specialized machinery to create durable, high-performance markings. Designed for highways and other heavily trafficked areas, Spotline delivers strong retro-reflection, especially at night, and under wet conditions. The PlastiRoute Spotline material is a paste-like, solvent-free cold plastic that cures through a peroxide initiator, ensuring long-lasting performance. During application, the marking machine lays down the cold plastic in an agglomerate pattern while simultaneously distributing fine drop-on beads. This advanced Spotline technique produces a textured Type 2 marking that enhances visibility, skid resistance, and overall driving safety. The repair process with chip fill begins by cleaning the pothole to ensure proper adhesion. A blower is used to remove loose debris, dust, and moisture from the damaged area, leaving a dry and stable surface. Once the pothole is clean, the operator pours chip-fill thermoplastic granules directly into the hole, spreading them evenly so the material fully occupies the cavity and follows its contours. The granules are leveled to match the surrounding pavement height and prepared for heating. Next, a heat torch is applied to activate the thermoplastic. As the material heats, it softens and begins to melt, bonding tightly to the underlying surface. The operator moves the torch slowly and consistently across the area to ensure uniform heating. During this stage, the chip fill settles and fuses into a single, cohesive mass that adapts to the shape of the pothole. The technician may add more granules if the material sinks while melting, then applies additional heat until the repair becomes smooth and flush with the road surface. After reaching the correct level and texture, the heated thermoplastic is allowed to cool naturally. Within a short time, it hardens into a durable patch capable of resisting traffic loads. The process concludes when the repaired area stabilizes, allowing vehicles to pass with minimal downtime. In this rock-cutting process, workers rely on simple but effective manual techniques. First, iron wedges are carefully placed in a row along the surface of the rock. Each wedge is driven into the stone using a hammer, creating pressure along the line. Once all wedges are set, the worker strikes them with strong, repeated blows. The combined force causes the rock to split cleanly along the line of wedges, effectively breaking it into two pieces. In some cases, the strength of the worker's hands and the hammer alone is enough to fracture the rock without using wedges. Skilled workers can apply precise, powerful hits at critical points, gradually forcing the stone to crack and separate. This method requires not only physical strength but also accuracy and experience to determine where to strike for the rock to split efficiently. This traditional rock-cutting technique, relying solely on basic tools and human effort, demonstrates how ancient and simple methods can still be effective in shaping and removing stone. By carefully positioning wedges and delivering controlled, forceful hammer blows, workers can break even large and hard rocks safely and efficiently, without the need for modern machinery or explosives. The concrete bunk slab at the cattle farm is constructed using the Slipform method, a continuous and efficient formwork technology. Initially, reinforcement bars are carefully placed along the slab layout to ensure structural integrity. Concrete is then poured into the Slipform machine, which moves steadily along the designated path. As the machine advances, it shapes the wet concrete into the desired profile, creating a smooth, uniform surface. The Slipform ensures precise dimensions and consistent thickness throughout the slab. Workers monitor the process, adjusting the flow and alignment as needed to maintain quality. After the concrete gains initial strength, the slab is cured to enhance durability and prevent cracks. This method allows for rapid construction of long, continuous bunk slabs, providing a stable feeding area for livestock. Overall, Slipform technology streamlines the pouring process, reducing labor and ensuring a high-quality, long-lasting concrete structure. The magnetic separator on the conveyor belt is an essential device used in industrial processes to remove unwanted ferrous materials from bulk mixtures. Installed above a conveyor belt, this separator efficiently extracts iron particles and other magnetic contaminants from various types of feed materials. As the mixture travels along the belt, it passes under the magnet, which attracts and holds ferrous particles, ensuring that only non-magnetic materials continue along the production line. This setup typically includes a strong permanent magnet or an electromagnet, positioned strategically above the belt. The magnetic field intensity is carefully adjusted to target specific materials, allowing for precise separation. In many industrial applications, such as in food processing, recycling, or mineral handling, this ensures product quality, protects downstream equipment, and prevents contamination. The conveyor belt system carries the material to the magnetic separator, where the separation process occurs continuously and efficiently. Ferrous particles adhere to the magnet and are then discharged into a separate collection area, often via a mechanical scraper or by the belt itself as it moves past the magnet. Operators can monitor the system and adjust settings according to the type and quantity of material being processed. Magnetic separators are highly versatile, available in different sizes and designs, and can handle varying material flows. Their effectiveness reduces maintenance issues, increases production efficiency, and improves overall safety. In modern industry, combining magnetic separation with conveyor systems provides a reliable, automated method for maintaining material purity while minimizing manual handling and operational interruptions. The assembly of the metal structure E5 at La Oliva, Horta Coslada, involved a mixed viaduct with a metallic trough beam. The project used 300 tons of structural steel to construct a total length of 142 meters, divided into 5 spans. One of the main spans, measuring 43 meters, stretches over the AP7 highway. The installation process took place between July 14 and 20, 2022, requiring precise coordination and heavy lifting equipment. Steel components were carefully positioned and secured, ensuring alignment and structural integrity. Each section was gradually connected. Welding and bolting elements were necessary. The operation demanded strict safety measures due to the height and complexity of the viaduct, showcasing an efficient and well-organized approach to large-scale metal structure assembly. The construction project at C4-Le-Plage involves the development of a modern marina designed to accommodate recreational boats and yachts. The work begins with extensive site preparation, including dredging, to ensure adequate depth for navigation and berthing. Reinforced concrete structures are then installed to form the quay walls and piers, providing stable docking points for vessels. Steel reinforcements are carefully positioned within the concrete to enhance durability and withstand marine conditions. The project also includes the construction of walkways and service areas, allowing easy access for visitors and marina staff. Specialized machinery, including cranes and piling rigs, is employed to handle heavy materials and ensure precise placement of structural elements. Throughout the construction, environmental measures are implemented to protect the coastal ecosystem, including sediment control and careful management of construction waste. Once completed, the Marina will provide safe and efficient mooring facilities, supporting tourism and local economic growth while enhancing the coastal infrastructure of Slipform.